Welcome to Module SU002 of Oricon's Upskill Modular Training Program devoted to Revit and BIM. This module is titled Structural Analysis Tools and is brought to you on behalf of Oricon by A2K Technologies. We will be using the purchased materials supplied by Oricon and A2K Technologies. Classroom notes and handouts are available for note-taking through the Exemplar portal. Throughout the training today, we will be covering the following topics: an introduction, conceptual form simulation, floor vibrations analyzer, gravity column designer, load takedown, static analysis of beams, frames, trusses, and slabs, composite design. Introduction. Revit not only provides the user with an analytical model to send data to dedicated structural analysis software, it also provides some embedded analysis functionality. This exercise is going to introduce the embedded structural analysis tools and how to operate them. All these tools have in common that independent verification has to be done prior to relying on the results. Some of the data input can be confusing and some modules display inconsistent results. Installation: where to find the tools. All tools in this module are available once Revit extensions are installed. Currently, they can be downloaded via Subscription Center. Only Composite Design is a separate installation file that can be found and downloaded via Autodesk Exchange, which is accessible via the X in the Info Center. Once the tools are installed, an additional tab with the Analysis drop-down in the extension ribbon appears. Prerequisites. Where applicable, the tools use the material definitions from the Revit model. Make sure that all elements analyzed have properly defined materials assigned. Load cases and combinations, loads and boundary conditions from the Revit model will be used to conduct calculations. Make sure that you are familiar with these tools from the Analysis tab. Also, the analytical model has to be consistent. To achieve this, the Analytical Adjust tool allows you to edit the analytical model independently from the physical model. The material parameter for beams and columns must be assigned as an instance parameter. When it is assigned as a type parameter, the tools won't start displaying an error message. Beams and column sections have to be recognizable by the tools. Most out-of-the-box families, as well as families from the content generator, which is part of the Revit extensions as well, will properly be recognized with all relevant physical properties. However, always double-check the properties in the analysis tools. The analytical model object styles from the standard Oricon template have been modified to allow better control of the analytical model. Units. Some of the tools only use imperial units. Find a conversion table from imperial to metric in Structural Plan View Level 1 Working. Other tools rely on the Revit project settings and therefore you can choose the preferred units to work with. Access the project units via the Manage tab. Codes and steel sections. All tools where design standards are involved use AISC design codes. Also, some tools only allow the use of AISC-conform steel sections to perform calculations. The content generator provides all standard sections, including information about characteristic static values. For an initial design outside US standards, the tools could be used to calculate AISC-conform sections and then replace them with local sections with matching shape and properties. Conceptual form simulation. Overview. This tool allows the user to conceptually analyze complex 3D geometries. It will display displacements and internal forces. Please be aware that this tool is not stable and tends to crash, depending on the complexity of the mesh as well as the loads and supports applied. The help file for this tool is misleading and some of the results are not accurate and contradictory. Also, the tool is only working in the family editor environment. It is not possible to analyze an in-place mass object. Therefore, all loads and boundary conditions need to be applied in the tool dialog. To follow this exercise, open the SU002 sample project model from the Open dialog box and open the standard 3D view. Select the conceptual mass in the background and open the conceptual mass editor by selecting Edit Family. Creating a valid mesh. Select the surface, hit Tab key, and use the tool Divide Surface to create the FE mesh as a base to analyze. Next step is to refine the accuracy of the mesh by selecting a number for the U and V grids. Also, and this is a very important step, we need to define a pattern. In the type selector, choose rectangle. The tool will automatically generate triangles from this setup later on anyway in the module. Please note that when using the form simulation tool on 3D geometry, make sure that the mesh is consistent around the edges. Start the conceptual form simulation tool via the extension ribbon under Analysis. We get two options. One is to consider only the current selection, which we could do, or to consider the entire project, which we will do. It doesn't matter in our case. This is the typical screen for all analysis tools. As a general workflow, go through the menu on the left, step by step. First of all, check and define the geometry and analysis conditions in various dialogues under the Data menu. Second, run and view the calculations under the Results menu. And finally, in the Report dialog, view and export a formatted report straight into Word or Excel or as an HTML MHT format for browser viewing. The Geometry dialog. In theory, this should allow you to define the thickness as well as material properties. However, in the current version, this tool only allows to change the thickness. Make sure you follow the following procedure to change the thickness, as it is currently the only way to update the thickness value. First, click on the number in the elements list. Second, change the thickness, type in 100. Then click on the element name rectangle. All other values like E modulus, lateral strain and weight will jump back to the default values as soon as the geometry is deselected. Go to the View tab up here, hit Selection and select the geometry again and see that the lateral strain 0.2 will always jump back to those default values, which reflect some sort of concrete. Supports dialog. Automatically generate pinned supports via the little icon at the top to support the structure. In this dialog, you can also select existing supports and change them to fixed pinned via the tab at the bottom, or delete them by selecting in the View window and hitting the Delete key. Please note that the plugin tends to crash when altering supports in this dialog. However, we hold down Control key, select all those supports here, apart from the outer ones, and hit Delete key on your keyboard to delete them. Cases and Combinations dialog. Disregard the Combinations tab, as at this time there are no combinations possible. Self-weight will be a separate load case, taking the proper self-weight from the geometry according to the geometric data, as well as from the material definition in the Geometry dialog. Let's add a vertical snow load with 5 kN per square meter, resembling a roof structure in Thredbo or on top of Mount Wellington. Set the following settings. Untick automatic wind load. Select snow as nature. Value is a vertical value, 5 kN per square meters. And hit add. Notice that little downwards pointing arrows appear. They are resembling the area load. The program automatically creates concentrated point loads on the mesh nodes according to the value we put in here. Loads dialog. Currently, this dialog is only for checking the applied area loads. There is no option to add concentrated loads or other independent loads. However, it gives a summary of total XYZ forces. Open the Planar Loads tab and notice that the total FZ value for snow is roughly 3000 kN. A quick check with our 20 by 30 meter roof structure and 5 kN per square meter verifies the expectations. Calculations dialog. Open the Settings in the View tab and select Legend as well as Values. Hit Calculate. Also check the tick box for deformation and review the results. Browse through the different load cases and result types. For example, displacement in Z direction. Be aware that the displacements in Z direction as well as the internal stresses show contradictory values. In the tab, maximum UZ is 482 millimeters, and in the graphical dialog up here, the minimum value is minus 147. Double checking the results with other FE software rather supports the values in the graphical view than down here in the tab. The minimum and maximum displacements are not acceptable anyway. So let's go back to the geometry dialog and change the thickness from 100 to 200 millimeters. Remember, first select element list, type in the value and then click on rectangle. Go back to calculations and run the calculations again. This time, minimum and maximum displacements are acceptable. As an option in the View tab, select Animate to animate the displacements. Be aware that this is currently very unstable and possibly causes your Revit to freeze. And this is why we won't do it. Report dialog. Be aware that the report will show a picture from the previously open dialog. When we go back to the supports dialog, orbit our model around, go back to the report dialog, the picture will resemble the one we have orbited around in the supports dialog. We can tick the boxes for the information we would like to find in the report. So we want all the information. Selected load case, the snow load case. Scroll down and have a quick look at the report. And then go to File and export the report to Excel, for example. This should open Excel in the background and create the report in Excel. Go back to Revit, as this concludes the exercise conceptual form simulation. Floor Vibrations Analyzer. Overview. The Floor Vibrations Analyzer for Revit is designed to analyze the vibrations response of steel-framed bays for human comfort and sensitive equipment criteria. According to AISC Steel Design Guide Series, floor vibrations due to human activity. Analysis of floors is performed in any of the three categories described by the AISC guide. First of all, vibrations due to walking, also known as static footfall excitation. Second is vibrations due to rhythmic activities, dynamic excitation. Third of them is disruption of sensitive equipment, or velocity limits due to walking activity. The help file for this module is providing detailed information about the AIC code used and assumptions made to perform calculations. Overview of the limitations. First of all, only four-sided rectangular bays are valid for analysis. As of AISC design guide, all bays must be completely covered by a concrete composite slab. This tool will not analyze steel-only structures. Ensure a composite Revit slab is used, similar to the one in the following example. Also, as of AISC design guide, the tool assumes that beams will act in composite action under service loads. Uniform floor loading assumed, points loads, etc. are not incorporated. Beams must be supported by girders. Walls as supports are not allowed. At the same time, supporting beams and girders must be wide flanged beams according to AISC standard. Non-conforming beams will be simply ignored. Exercise. To follow this exercise, open the SU002 sample project from the Open dialog box and open the standard 3D view. Zoom into the area of the steel platform. Select the slab on top of the platform and start, via Extensions Analysis, the Floor Vibrations Analyzer tool. Please note that floors to be analyzed have to be selected prior to starting the tool. Hover over the floor in the Floor Plan dialog and see that the tool automatically finds the supporting beams and girders, slab thickness, and displays the geometric information on the right. Note that all units are imperial in this tool. This can't be changed. Refer to Introduction for unit conversions. Open the Analysis dialog and set the settings to circumstances that are best matching your case. For this exercise, set the settings to the following. We tick walking excitation, rhythmic activity, aerobics or jumping. Leave the affected occupants as they are. Tick sensitive equipment and click on Auto. In this dialog, select Computer Systems, hit OK, which gives us a defined value for the velocity limit. Leave the other options as they are. In this tool, the calculations are conducted in the background. Go back to the floor plan, hover over the floor and check if the results are acceptable or not. In this case, have a look at the bottom right. The vibrations exceed the definitions in the AISC for all three cases to be checked. The options now are either to increase the slab thickness or to use stiffer beams or girders to minimize deflection and therefore improve the natural frequency of the bay. We choose the option to swap the existing girders to stiffer ones. Hit Close and start the content generator from the Extensions tab, Tools. Go to the File menu, Regional Settings, and make sure that under Profiles, AISC Pro profiles are loaded into the module. If it's not, click on Add Database to the list to add additional databases. Hit OK and select W for wide flanged beam. In here select W18 by 60. Untick columns as we only want to generate framing elements and hit OK. We now swap the two weak existing girders via the type selector to the stronger ones we've just created via the content generator. Select the slab again and run the floor vibrations analyzer. Go to the Analysis tab and set the settings as previously. Go back to Floor Plan, hover over the slab, and find that the result is only positive for walking excitation. We could now continue the iteration process with different girders or beams or slab thicknesses until we are happy with the results. We'll leave it as it is and open the Report dialog. This dialog allows us to create two different types of reports and either print the report or save the report as an HTML file. And this concludes the exercise Floor Vibrations Analyzer. Gravity Column Designer. Overview. This tool allows us to design isolated wide flange, HP and HSS columns. The design is conducted according to AISC 13 LRFD interaction equation method. Please find details about the calculation methods and assumptions in the help file by hitting F1 key while in the module. Note that all units in the Gravity Column Designer are imperial. This can't be changed. Refer to Introduction for unit conversions. This tool will only take point loads from the Revit model into account located within 30 centimeters eccentricity along the axis of the column. However, tributary loads or loads defined as is-reaction in the instance properties are not considered. Unfortunately, this limitation includes loads created by the load takedown module from the Revit extensions. The column designer in its current version only allows to design columns to the conditions at the column top. Additional loads and moments can be applied in different levels, but they won't affect the results. This is a bug and used to work in previous versions. As a result, the following exercise will only focus on the column top. Exercise. To follow this exercise, open the SU002 sample project model and open the standard 3D view. Zoom into the example building and select the central east-facing column. Notice that several point loads resembling tributary loads have been applied manually. Start the Gravity Column Designer from the Revit Extensions tab. In the Summary dialog, the tool displays geometric and material properties as well as whether the selected column is adequate according to the design method with the current settings. Select Level 3 Column Top dialog to check existing loads and to apply actual point loads with eccentricity in X and Y axis as well as a load type. Type in the following details: XY offset for both loads, dead and live, to 10 inches. No additional moments required as they are covered by the eccentricity of the point loads already. Both X and Y axes are pinned and sideways constrained. Check the summary at the bottom right. Select Level 2 and Level 1 dialogues and set the XY constraints to pinned and sideways constrained. These settings will affect the column top results. Go back to the Summary dialog and select Optimize Section. The software will select the smallest section with an interaction result closest to but not exceeding 1. Note that you can select the section types and families that are accessible for the Gravity Column Designer in the Family Locations dialog. Open the Report dialog. This dialog displays a report about the calculation environment and lets us either print or save the report as an HTML file. After creating a report, select OK and notice that the column has changed to the optimized section. And this concludes the exercise Gravity Column Designer. Load takedown. Overview. The load takedown extension performs a simulation of load takedown for vertical forces defined in the Revit model. The tool always distributes loads evenly and does not take the stiffness of slabs or load distribution of continuous beams into consideration. Tributary areas are simplified and always distribute loads with a 45-degree angle. Even though that by Revit definitions slabs might be spanning in one direction only, the tool always distributes loads into multi-directions. Point supports from the Revit model are used in this tool. Linear supports as boundary conditions for walls are not recognized by the tool. Only wall foundations are recognized as supports automatically. However, the tool offers the option to manually add or refine the supports within the load takedown interface. The load takedown tool uses the material property for the density or unit weight from the model. Ensure that the material definitions are properly assigned for the elements selected for load takedown. Resulting point loads and forces on supports can be written back into the model as reaction forces. Unfortunately, the other analysis tools, for example the Gravity Column Designer, can't use this information. Exercise. To follow this exercise, open the SU002 sample project file from the Open dialog box and open the standard 3D view. Zoom into the area down here and select the whole structure. Use the filter tool to filter out all point loads. These point loads are tributary loads and were applied for the Gravity Column Designer exercise. Delete them, otherwise they will end up in the load summary. Select the whole structure again and start the Load Takedown module via the Extensions tab. In the following dialog, we select to consider only the current selection and define that the self-weight of the structure has to be added to the dead load 1 load case. Hit OK. When steel sections are part of the geometry, a database dialog pops up. Add AUS and AISC to the active databases. This will allow the tool to find the correct section properties according to the selected standards. Click Apply. In the Geometry dialog, under View, select Selection and select different elements in the View window. Notice that the element properties according to the Revit model are displayed at the bottom. There is also an option to only display elements assigned to particular levels. But this does not necessarily work too well for elements spanning over several levels. Switch back to All. Open the Supports dialog. If the model is not properly defined with all necessary supports, additional point and linear supports can be created via the small symbols at the top. This is also a good place to verify the model integrity. Select the little green tick button, which produces a list of warnings, which in this case we can ignore. The Load Cases and Combinations dialog, as well as the Loads dialog, only lists all in Revit defined loads, load cases and combinations. The options we have in the Loads dialog is to select particular loads and delete them if necessary. Via the Structure menu up the top, we can also reduce live loads according to standards. Once we are happy with the structure and the load settings, we open the Structural Analysis dialog. Click Calculate. A warning dialog appears, which is telling us that 2 loads will be ignored in the calculations. Those 2 loads are horizontal wind loads, which we can accept to be ignored for load takedown. Select Close. The Structural Analysis dialog offers to set different options to explore the results. We can select different load cases or combinations, etc. To display dead load forces on the foundations only, choose case dead load 1, the whole structure, And under Results, Loads on Elements, select Concentrated Forces and only on foundations. This gives us an overview about the resulting forces on our foundations. Open the Report dialog and notice that the picture for the report is according to the settings set in the Structural Analysis dialog. Go back and untick only on foundations to view the whole structure. Select Report again and tick the boxes for the geometry, results and load cases you would like to find in the report. Once you are happy with the report layout, we can either print or save the report as an HTML file. Other options are to export the report straight to Excel or Word. Export the report to Excel via the File menu. Excel will open up in the background with all the report information included in a new sheet. Go back to Revit and select the Save dialog. This allows us to create reaction forces in the Revit model according to the load takedown results. Select the following options: Save loads acting on foundations, dead load and live load, untick wind, as we don't have any wind loads, and hit OK. Notice that additional resulting point loads on the foundations are created in the Revit model. And this concludes the exercise Load Takedown. Static analysis of beams, frames, trusses and slabs. Overview. The 4 static analysis tools can be used to get an idea about stresses and displacements in substructures of a Revit model. For calculations, the modules are using general structural physics and no codes. The static analysis modules do not verify whether the analyzed elements fail. They simply reflect results from elastic first-order theory analysis. The modules will recognize the structural definitions from the analytical Revit model. They also offer the option to change existing, apply additional, and delete unnecessary supports and loads. Take particular care in defining loads, supports, and bar end releases properly. This can be done either by adjusting the Revit analytical model or by changing definitions in the analysis dialogues. Loads must be applied directly on the analytical lines or faces of selected elements. Tributary loads from connected elements, for example beams on girders, are not automatically recognized. Reaction forces created from the load takedown module are not taken into account either. The 3 modules for analysis of beams, frames and trusses work similarly. Therefore, the following exercises only guide through a frame analysis example and a slab analysis. Exercise Frame Analysis. To follow this exercise, open the SU002 sample project model from the Open dialog box and open the standard 3D view. Orbit the model to the top right position by clicking on the view cube. Select all objects from the south-facing framing elements by opening a selection rectangle from left to right. Hit HI on your keyboard to temporarily isolate the selection. Make sure that the selection looks like this. Before analyzing the frame, we need to apply some additional dead loads and live loads. Select the Loads command in the Analyze tab and choose the hosted line load. In the type selector, select Framing Load, which has an adjusted force scale so that the symbols displaying the loads are appropriately sized. Add dead load with -10 kN per meter on the joists and -15 kN per meter on the central girders. Do the same with the live load case and add 15 kN per meter on the top and 20 kN per meter to the central members. Select all elements and start the Static Analysis of Frames tool from the Extensions tab. In the appearing dialog, select deadload 1 as the load case to add the structure's self-weight. The Geometry dialog offers the option to double-check the geometry. Select individual framing members. All relevant element properties for this static analysis are displayed at the bottom of this dialog. Open the Constraints dialog and find that there are some redundant supports. They are reflecting connected girders and joists from the model. Select and delete the redundant supports one by one. The nodal support list at the bottom of this dialog offers the option to change the support definitions. For example, change them from pinned to fixed. The Releases list provides information about the end releases of all framing members. These definitions are read-only. If they are not reflecting the physical model, changes have to be made in the analytical system of the framing member in Revit, and the tool has to be restarted. The Cases and Combinations dialog displays a summary of all in Revit defined load cases and combinations. Loads dialog. Select a load case and click on any of the loads in the view window to display the load properties graphically. At the same time, the selected load gets highlighted in the loads list at the bottom. The loads are read-only as well and need to be changed in the Revit model if necessary. Open the Calculations dialog. As soon as this dialog is selected, the calculation is performed and the results are accessible. Explore the results and add forces to the view settings. Change the load case to Wind 1 and tick Internal Forces N to find that all 4 bracing elements suffer from axial force. Unfortunately, this module does not allow for the definition of conditions that prevent braces to fail on compression. At the same time, we can't disable particular bracing elements for calculations. Therefore, we would have to hide the bracings that are under negative axial force in the model temporarily and restart the tool. In the Edit menu up the top, select Characteristic Point and place a few of them in the model. The calculation results at the characteristic points can be displayed in the According tab. Open the Report dialog and select the information to be included into the report. Via the File menu, you can save the report out as an HTML file, print or export to Excel or Word format. To finish the static analysis of frames exercise, select OK. In the 3D view, hit HR on the keyboard to reveal all previously hidden elements. Exercise Static Analysis of Slabs. In the 3D view, select the 200 mm concrete slab, including supporting walls and applied loads. Hit HI on the keyboard to isolate the selection temporarily. Select the slab only and start the Static Analysis of Slabs tool from the Extensions ribbon. Explore the slab properties in the Geometry dialog. Note that openings, provided they exist in the Revit model, are recognized by this tool. Open the Constraints dialog and find that the current settings for the nodal supports are reflecting pinned supports, whereas the edge supports reflect a fixed monolithic wall connection. This suits our model perfectly fine for now. Please note that the tool mixes up releases around the X and Y axis. When Rx is released in the dialog, it is actually Ry that reflects the release in the calculations. Cases and Combinations dialog displays a summary of all in Revit defined load cases and combinations. Loads dialog. Select the Live Load 1 load case and click on any of the loads in the view window. The loads are read-only and need to be changed in the Revit model if necessary. Open the Mesh dialog and generate a mesh with a maximum element size of 500 mm. In the Edit menu, select Emitter and define the minimal size of 100 mm. Click in the View window on the top central supporting column to refine the mesh. The emitter will show up in the tab at the bottom. Select Generate again to regenerate the mesh with the new definitions. Open the Calculations dialog and select Calculate. Explore the different results from different load cases. Select the Edit menu and place a few characteristic points in the View window. These characteristic points with calculation results show up in the tab under Internal Forces, Characteristic Points. Open the Report dialog and select the information to be included into the report. Via the File menu, you can save the report out as an HTML file, print or export to Excel and Word format. To finish the static analysis of slabs exercise, select OK. And this concludes the exercise Structural Analysis Tools. Composite Design. Overview. The Composite Design tool for Revit can be used to design composite floors according to AISC standards. It is complex to use and imposes several restrictions on the geometric and analytical setup of the Revit model. At the same time, the tool is also very powerful. One of those restrictions is that only AISC standard wide flange steel sections can be used. The content generator from the Revit extensions can be used to access AISC-conform wide flange beams. The comprehensive help file is pointing out detailed instructions on how to set up the model to use this tool reliably and efficiently. It also provides information about the standard, formulas, analytical considerations, and usage. The help file is accessible by hitting the F1 key while in the module. Also, ensure that proper material definitions are applied in the slab definition. Otherwise, an error message will appear and the tool won't start. Exercise. To follow this exercise, open the SU002 sample project model from the Open dialog box and open the standard 3D view. Select all elements from the sample building and use the filter tool to select and delete only the 4-point loads. They are not necessary for this exercise and prevent the Composite Design tool to start. Click on the right side of the view cube to select the composite slab, including all applied area loads and supporting beams comfortably. Hit HI on the keyboard to isolate the selection. While all elements are still selected, start the Composite Design tool from the Extensions ribbon. The Geometry dialog is displaying the geometric and material properties of the selected element. Beams are colored according to their utilization ratio. This ratio is determined by calculations according to AISC, but also by the settings defined in the Composite Settings. Select Composite Settings in the Edit menu and browse through the 4 different tabs, allowing you to adjust the calculation environment. Leave the settings as they are and hit OK. Open the Cases and Combinations dialog, which displays all load cases and combinations according to AISC standard for composite design. Proceed to the Loads dialog. This dialog is showing the loads considered for the framing member that is selected in the View window. The tool automatically transfers the external loads from the slab onto the framing members below. Static calculation reveals detailed information about calculation results, including moment diagrams, etc. Select the center beam in the View window and browse through the results. As with most other analysis modules, you can apply characteristic points via the Edit menu to show the results at interesting points. Select the Beam tab and add a couple of characteristic points. The Extreme Results dialog offers a quick overview about minimum and maximum displacements, internal forces, as well as reactions. Open the Design dialog and select Design all beams. This will run through all AISC-conform wide flange beam sections and select the best matching section for each individual element according to the defined composite settings in the Edit menu. Once the design is finished, open the Report dialog to produce a report for each separate framing member. Select a member in the selection window, open the Report tab, and choose the information to appear in the report via the tick boxes. Preview the report and, when happy with it, select File menu to either save the report as an HTML file, print, or export straight to Word or Excel. To finalize this exercise, select OK to apply the optimized beam sections to the Revit model. Notice that the Revit model updates automatically according to the optimization results in the Composite Design tool. And this concludes the exercise Composite Design. And this concludes the module SU002 Structural Analysis Tools.